Okay, so the recording has started. Now I'll share my screen. So hello everyone, like this is week 6 of NPTEL CS52 reinforcement learning course. I'm Sandarbh and generally these sessions are on Tuesday. Last week was an exception, week 5, because like it was preponed to Friday. But from now on, like it will be mostly on Tuesdays on the same link. And these are the usual details, like anyone who has taken this course can join. And basically like there will be discussion on practice assignments, then assignment also, and some problem solving which won't be part of practice assignment and assignments, and also some doubt clarification. And these sessions are to ensure two-way communication. So expectation as usual is that you have watched the weekly lecture videos of like week 6 and at least made an honest attempt on the weekly assignment and practice assignment, and it is as usual recommended to read the book. So like after like this week, like you should have read chapter 5 and 6 of the book, and like the slides and recordings are getting updated in the same like spreadsheet. So again, like we will follow the same order: practice assignment, then problem solving, demo. So today's demo will be on q learning and sasa. So these are like two of the most popular reinforcement learning algorithm. This is the most popular, and Sasa is the second most popular. And then the assignment. So in assignment, as usual, I won't give you the exact answers, but I'll guide you through. And these are the big 6 topics of policy Monte Carlo, and then this upper confidence quiz, then TD0. So TD0 is basically one member of this bigger family of algorithms called TD lambda. So in week 7, like this bigger family will be introduced, and like this lambda can take value, like it can take 0, it can take 1. So like this general family will be introduced in week 7. And TD0 control, then in this we studied Q learning and SASA. Again, like for Q learning, we had a separate video, and then after state. So in this, the concept of like two opponent or maybe nature makes its moves also. So that after state concept was also introduced. So before moving to like our usual content, I'll like to mention one thing. So basically, like last week, like I went to a workshop which was actually on RL itself. So in RL, like what are the recent events, like what is the current research areas which are like popular, and also the future direction. So this happened at IISC, and luckily like they have like made the recordings available on their YouTube channel. So you just have to search, this is the computer science department there. Just search CSA IISC and then go in the live section. You will find the recordings of those videos. So most of the content, like most of the lectures were on, talks were on bandits. So I think like you will be able to grasp those, and some were on RL. But either way, like since you have studied Q learning and Sasa, you will be able to catch up most of them also. So uh, I'm not saying that you should go and watch, but it's highly recommended that you can watch those sessions also, just to improve your knowledge of RL. So now let's begin with the practice assignment 6. Before that, like if there is anything for me from the audience, you can ask me. Like otherwise, like I'll move to the practice assignment. Okay, then I'll start with the practice assignment. So the first question is, consider the following equation for TD control. So they have given us an equation where this is the new estimate. This is the old estimate, also called as current estimate. And this is usual alpha, which is the learning rate. And they have given us, so basically like they are asking which part of the equation is known as TD error. So is it like this part, like what is this entity, RT plus 1 plus gamma times like current estimate or old estimate, you can say. So this is not like TD error, right? This is called as target. So this is the target. And is this the TD error? No, because like there is an extra learning rate coming up, right? This alpha. So basically like whatever is inside the these brackets is known as TD error. So this is the like third one is the right answer, right? So if you multiply by learning rate also, you get something which is called at update. So this is basically the updates. You are adding this update to the old value of Q and getting the new value. With learning rate, you can call it update. And this entity which I have underlined is the target. This is the old estimate. So basically our like TD error is like target minus current estimate. So this is known as TDL. And again, like this doesn't make much sense. Like it's on different states and different action. So this is definitely wrong. So this is the answer. I think like if you have studied the equation, like update equation of TD, then you will be able to get this one right. If there is any doubt, you can ask me now. Otherwise, like I'll move to the next one. Okay, so in this they have asked which of the following statements are yeah.
There is some Q parameters seems to be missing. It seems, no, sir. No.
Where?
Q world at gamma world.
At gamma
Just
old.
typo, sir. Typo error.
Where in which
At
option? Are you talking
at C option only? At C option only.
Okay. Yeah. Okay. Yeah. So
Just typo.
yeah.
Yeah.
Oh, yeah.
Yeah.
So basically
Sorry
you
for the
get
interruption.
no issue.
That's okay.
Yeah, I also missed this. So I was
That's okay.
expecting like it will be the same equation. So yeah, that is a typo. Okay. So this is like two like there are four options. You need to select which of the following are true. So circles means only one of them is correct. So which of the following are true for TD0? And they have given us the assumption that assume that the environment is truly Markov. So on the basis of that, like we have to answer which of the following is true. So it uses the full return to update the value of states. Does it use the full return? No, right? So it uses simply like one step return, right? Like reward, this is its targeting, like we saw in last equation also, right? So just reward plus gamma times. So this is like one step return. If it was like plus gamma square, then it would have been two step return. And in similar way, if we would have continued, then it will be n step return if for n steps. So we are not using full return. Full return means till the end, till you terminate. So basically we are using just one step return. So this is wrong. Now both TD0 and Monte Carlo policy evaluation converge to the same value function, giving a finite number of samples. So if finite number of samples are given, we know that from the lectures that they won't converge to the same solution. So basically like this TD0, it converges to something else, and Monte Carlo basically converges to a minimizer of squared error. And what does TD converges to? Anyone knows? Or maybe write in chat, I'll check in chat once. Let's see how much you remember.
Monte Carlo requires infinite number of samples, sir. Means it requires until the.
So it basically like even with finite number of samples, Monte Carlo will converge to minimizer of squared error. Because like if you give finite number of samples, so on the basis of those finite number of samples, whatever squared error will be there, it will converge to that. And if you give infinite, then you can calculate in limit, like what is the square error, and it will converge to that. But TD0, like it basically converges to something called as certainty equivalence. There is a model in OR theory, which is called certainty equivalence model. So it converges to this, and this is basically Markov. So our assumption, like they have already given in the question, assume that that environment is truly Markov. So since these two are converging to different entities, like we cannot say that they will converge to same function given a finite number of samples. So this is also wrong. But in the third option, it's given like the same statement, but we are given an infinite number of samples. So this is true because if you are given an infinite number of samples, so these two will become equivalent of each other. So they converge to the same thing. So option C is the correct option. And in fourth option, they have given that TD error is given by V new minus V old. This is not. This is simply the update, right? So we can write V new is equals to V old plus update. And this update also comprises of this learning rate, and this is multiplied by TD error. So this is like based on last question only. So I hope like you got this. What like if we are given an infinite number of samples, then only like TD0 and Monte Carlo policy evaluation will converge to the same value function. Okay, then I'll move to the third one. So this is with respect to weighted importance sampling, also called as normalized importance sampling. Okay, so this is the usual uh, equation of weighted importance sampling, and this factor is known as importance factor. So xi is the trajectory, fxi is the return on the trajectory. Okay, so they have given these are the usual notations. Pxi is the probability of trajectory xi when following policy pi. Okay, and qxi is the probability of trajectory xi when following policy mu. So they are basically asking what is pi and mu. So is pi the estimation policy or pi is the behavior policy? So basically, like in any form of sampling, we want to estimate the estimation of this estimation policy only, right? Pi. So P corresponds to pi, and pi is basically the estimation policy. You remember, like if we consider only the normal sampling without any important sampling, then this factor was only introduced so that we can like compute with respect to behave with respect to some easier policy, maybe random policy or something. And then on the basis of that, we can do something called off policy update. And if we do like correctly with this importance factor, these are like similar entities. So the correct option is pi is the estimation policy. This is the policy for whom like we want to estimate this value, right? Value of some state, maybe some starting state. And mu is the behavior policy. So with this, like we are kind of generating the data. So all those like data, if you consider this as one data point, state you took the action, what reward you got, and what is the next state. Data is getting generated through this behavior policy. So the correct answer is pi is estimation policy and mu is the behavior policy. So I hope you got this. If there is any doubt, you can ask me. Otherwise, I'll move to the next question. Okay, then I'll move to fourth one. So fourth one says that so it's a assertion reason. SASA is an on policy method. So you should be knowing this. Like SASA is a on policy method or off policy. Maybe write in chat. Okay. So SASA is an on policy, and yeah, right. So what is actually off policy? Off policy is Q learning, right? So Q learning is the off policy one, and SASA is the on policy. So this is true. Like assertion is definitely true, and the reason for this assertion they have given is in SASA we do not update the action that was actually used, so it is on policy method. Like this is not the definition of on policy, right? In on policy, we update the same action which was actually used, right? So this reason is false. Although assertion is true, so assertion is true, but the reason is false. Because like in on policy, we update the same action. You remember in SASA algorithm, like we were using the same action and then in the loop it was there and it was getting up. So same action was there. So that is what it makes it on policy. But here in like reason they have given the converse of it. So this reason is false. So the correct option is option C. Okay, then I'll move to question 5. So again, like this is multi-correct since there are squares. So which of the following statements are true? So does learning require, so first option is learning requires at least a simulation model or planning requires at least a simulation model. And learning can be done just using the real world samples. Planning can be done just using the real world samples. So in planning, like if you forget about RL, like you consider general planning, like how human beings plan. Like when you plan, you like basically imagine the possibilities in future, what could be the possibilities, and on the basis of that, you take some decision that this possibility is maybe its chance of happening is higher. So maybe you assign greater weightage to that one. And on the basis of that, you aggregate them and take some decision. So planning kind of requires a simulation model, right? So planning requires at least a simulation model. So this option is definitely correct. But learning can be done using just the real world samples. Because like learning, you don't need to see like what could have happened. You will simply see like what is actually happening in the real world. There is this, suppose this is our agent and this is our environment. So the job of the agent is just to take the action and the environment will come up with the next state and reward. So this loop continues. So learning can be done just using the real world samples. For learning, we don't require simulation model, but planning requires a simulation model. Suppose if we are doing Monte Carlo planning or even like the algorithms which were discussed in last week, like value iteration, policy iteration, all these are planning algorithms. And learning algorithms are like something like Q-learning, SASA. So like learning is also called as control. So planning requires at least a simulation model and learning can be done just using the real world sample. So option B and option C are correct. And this basically makes option A and option D wrong. So I hope like you have no doubts in all five of these questions. If there is any doubt, you can ask me now. Otherwise, I'll move to the next segment. Okay, then I'll move to problem solving. So in problem solving, like we have the first question. In the search procedure listed in the Monte Carlo tree search, so they are talking about MCTS, which is or are the uses of the depth parameter. So, okay. So basically like this is multiple option correct. What is depth parameter? So suppose we are at some state S and we want to estimate its value. But sometimes this happens usually in games like chess. Like the trajectory which we can obtain, like suppose terminal state, we can think like suppose win, lose, or draw. These three terminal states are there. So suppose if so, it takes a like lot of time, lot of moves to get to this like win state or lose state or whatever. Like basically, I'll refer it as T terminal state. So sometimes what happens is we do like we don't plan till the absolute end. We do some kind of bootstrapping. So we plan till some depth D, and after at that depth, whatever node is there, we substitutes its estimated value. And in this way, like we do this MCTS with depth factor. So this depth factor is important because it kind of helps us in like suppose if we have limited computation, right? We cannot like we don't have the resources to compute all the way till the end. So we can compute till some depth, and on the basis of that, we can take our decision, whichever is the best action. So this usually happens in like in human beings. Suppose if human beings are playing the game of chess, you don't think till the end that how you will checkmate the king or something like this. You maybe think a few steps further, like whether if you move your pawn up and your maybe rook will move in some direction and then you will do this, maybe 5 6 steps. So you plan like 5 6 steps ahead. So this is like the importance of depth factor. In a similar way, like this depth factor was introduced in MCTS, but like here, like human beings are basically limited by their cognitive power. So basically, we cannot afford to do that much computation because chess also has a limit. Like you have to make your move in some amount of time. So we can actually do till only few steps. And with computers, we can do till the end, but the search space is sometimes so big that it becomes infeasible to search till the end. So we introduce this depth factor here to basically save our computation power also, and also to like give the answer in the like whatever stipulated time is there. So the question asks like which of the following are uses of the depth parameter? So allows us to identify leaf states. Yes, this is true because leaf state is this leaf. So this is the terminal state and this is leaf. Leaf state, you can say like wherever like at what state we plug in the bootstrapped value. So that is called leaf state. So it allows us to identify the leaf state. So maybe on every trajectory you can go till depth deep and say this is the leaf state. So it allows us to identify, but does it allow us to identify the terminal states? We don't know because terminal state might appear much after the leaf states. So this is wrong, right? It can be used to impact the choice of action selection. Yeah, definitely. If you like are doing till a depth of 10, you might be planning better if you like compare it to if you are planning just two step ahead. So it basically affect our choice of action also, because like if you are planning further down, then you might be able to have more data and see like what is going on at the 10th step. If you are planning just short term planning, like the action might be different in this too. So it can be used to impact the choice of action selection. So this is also correct. And it allows us to specialize value functions based on the number of steps that we have taken. Yeah, so basically like suppose if we are going till d def, and after d steps we are plugging in the value function value, so in that node. So it does this also. So these three options are correct. Second one is wrong. Is there any doubt in this? Okay, then I'll move to the next question. So suppose you are given a finite set of transition data. So this word finite is important here, because you know like how we have already seen one question in which finite and infinite made the difference. So you need to keep these points in mind. Suppose you are given a finite set of transition data, assuming again second assumption is Markov model. So that can be formed with the given data as the actual MDP from which the data is generated. Okay. So they are saying like, suppose if you are given some transition data, suppose this transition. So this is one transition. So you might be given maybe some set. Suppose n transitions are given. Maybe I can index it like I plus one, something like this. And you can index these also. I. So in this way, like you are given some transitions, and what they are saying is that the MDP like which you will obtain from this set of transition data like is actually the actual MDP from which this data is generated. So sometimes what happens like if our samples are not unbiased, like there might be some bias, so we might not get the same MDP from which it was generated. And this we saw in Bandit's case also. Like in Bandit's, suppose the true distribution of harm was like 0.7 probability it was getting head, and with 0.3 it was getting tail. But when we were sampling, like it wasn't like every time like we sample like suppose if we sample 10 head 10 times the point, then like 7 times head, it wasn't necessary. Sometimes we were getting 8 times head or even 6 times head, and in this way like, so that model might not be actually equal, but here they have given us the fact that it is actually equal. So now the question is, will the value function calculated by the MC and TD methods necessarily agree? So important thing which I mentioned already before is this finite data. So in finite data, we know like these two, like MC and TD, although MC will definitely converge to squared error minimizer, but this TD will actually converge to this Markov model. But the issue is like, will these two be equal? We cannot say that with finite data, because this MC may converge to squared error and this squared error minimizer might be different from the actual MDP. So here, like the major issue is arising because of Monte Carlo, not because of TD. Because for TD, they have given that it is actually converging to the same MDP. But either way, like with finite data, we cannot say that. So the answer is no. So we cannot necessarily say it might happen, but we cannot always say that this will always happen. Okay, so I hope this is clear. Now I'll move to the next question. So this question is concerning iterative policy evaluation. So yeah, in this we have seen the use of different update equations in DP, MC, and TD methods. With regard to these update equations, so DP and TD methods make use of estimates but not MC. TD, so basically like they are saying which of these methods make use of estimates. So estimates are basically like after like some point, like some traversing into the trajectory, we reach some state and we plug this value of that state, right? V of that state. So like in which of these methods like we do this? So in dynamic programming, like you remember the Bellman equations. right? In Bellman equation, either way, like we were summing over the all the transition next states, and if the policy was stochastic, then we were summing over all actions also. Like there was this pi a, and there was this transition probability if I denote by as a as that, and then there was this step reward plus gamma times, and then we were plugging the estimate, right? V pi of the next state. So in dynamic programming method, we were using the estimates. Yes. TD methods, definitely. Like we saw the equation before, like it uses one step estimate. So after one step, like we were plugging in the value. But what about MC? Can we plug the estimates in Monte Carlo methods also? Yes, we already saw this, right? So it's not necessary to plug, but I mentioned this example. Where was this chess example? So yeah, this chess example, you can go till the end, but if you don't have the computation power to go till the end, then you can plug in the estimates. So even in MC methods, we can plug the estimates. So all three methods make use of the estimates. So I hope this is clear. Yeah, now I'll move to the next question. So next question says, is it necessary for the behavior policy of an off policy method? Let's denote this behavior policy by mu. This is the usual notation. And pi is the policy estimation policy. So the question they are asking, is it necessary that for the behavior policy of an off policy learning method to have non-zero probability of selecting all actions? Does it need to be non-zero? See, maybe you'll remember this way. Suppose some action is there. So in off policy methods, we will be using what is called as importance sampling, right? So in importance sampling, there was this term, right? Pxi upon Qxi. So due to this term, like this ratio, we don't want it to be zero, right? Otherwise things will become worse. It might go to infinity. But is it always that we should be having this? Is it necessary? So they are saying that is it necessary that this denominator always has to have to be non-zero? No, really, because like if we have something like it has to be non-zero if the numerator is also non-zero, right? If we have 0 by 0 thing, like then it's fine. We can replace it by 1. So necessary? No, you cannot say it's necessary. And if it was like to have a non-zero probability of selecting all actions provided, like this is also numerator is also non-zero, then definitely yes. But if they haven't mentioned that, then it's not necessary always. So the correct answer is A. I hope like there is no doubt in this. Now I'll move to the next question. So this question concerns expected SARSA algorithm. So expected SARSA and is exploration, suppose using Epsilon greedy or you can use softmax also, but so basically is exploration required as it is in normal SARSA and Q learning algorithms. So SASA, like we were doing on policy, right? We were doing off policy. So here target was having some max term. Here, since it was on policy, so we were using the same action. But in expected SASA, we were having some this summation over all the actions and like whatever probability of those actions. So the question is like, is exploration also needed in expected SASA? What is the answer? So like the answer is the yes, either way, like you will need the exploration because like if you don't have exploration, suppose in update terms, there is this target. In target, there will be this sigma over action. But using the sigma, you will be updating some action, right? And this update will happen on this action, but you need to explore other actions also. Those also need to be updated. Suppose there is second action a dash. If it's never like part of the policy, initial policy which you began with, then you will not explore this action. You might not explore this action. So exploration is always needed so that you can try out different actions also and update their Q values also. So even in expected salsa, although like it might appear that the term includes sigma, but that term is used to update this Q value of corresponding to this action. The Q value is corresponding to some other action. This will also use this sigma or overall actions, but this might not get updated. It might be suppose if our uh, table is like this. Maybe here states and actions here. So if we are following like some policy, then it might be possible that you are like kind of updating these or these trajectories only. But these at the corners, these actions and state pairs might not get updated. So it is necessary that you explore all the actions, even in expected also. So I hope like this is clear. Okay, then I'll move to the next question. So here the assumption is we have a simulation model available for a problem. To learn an optimal policy, instead of following trajectories end to end in each iteration, we randomly supply a state and an action to model and receive the corresponding reward. So what they are giving is S, A, and R. This information is used for updating the value function. Okay, so which method among the following would you expect to work in this scenario? Will it be SASA? So what you are giving is you are giving maybe at every iteration. Suppose if there are I number of iterations, I is equals to 1 to I. And so which of these method will work in this scenario? Like will it be SASA, expected SASA, or Q learning? Or option D, none of the above. Like something is missing here. You need to know. So yeah, someone in chat maybe answer. So someone asked this question, why do we need both estimation policy and behavior policy? So the answer for this is like sometimes it's hard to estimate some policies. Some policies like are very hard to estimate. They're like that function, Q value function is hard to estimate. So we use like a simple behavior policy. Like suppose if you are generating data according to a random policy, and then you can simply do random kind of actions. You can take random actions, and on the basis of that, you can estimate the behavior, like estimate the policy, which is tough to estimate. And this all this through importance sampling. So this is the reason why we use behavior policy. And this is the concept behind importance sampling also. If some distribution is there which is hard to estimate, then we use some other distribution to estimate that distribution. So yeah, so the answer for this question is none of the above because one thing is missing. See, when I mentioned that one transition should be like this next state is not given to us. If next state is like one component of the data transition is missing, then how can none of this algorithm will work? Not SASA, not expected SASA, not even Q learning. None of them will work because we also need to be supplied this as the next state from the environment. So suppose you are in state S, this is agent, and you take some action, the environment will give you next state and reward. But if this next state is not given to you, then none of these algorithms will work. So this is the one atomic entity like which cannot be divided. So you need to have at least this transition, like these four components: state you are in, the action you take, the reward you get from the environment, and the next state you land in. So these four components should be there in every transition. Otherwise, you cannot use any of these algorithms. So I hope it's clear. So someone wrote like we need TD. So yeah, like TD, all these are TD algorithms only, but that one component was missing. So without that, even like these TD methods won't work. So these three are TD control methods only. So now I'll move to next question. So this is actually calculation based. So it's good that you practice some of these because like these questions might be there in the exams. So consider the following transition. So we are given, so this is like you can say episode 1 and this is episode 2 for an undiscounted MDP. So undiscounted MDP means gamma equals to 1. Don't make this mistake that undiscounted means gamma equal to 0. Undiscounted means gamma equal to 1, right? With two states P and Q. Okay. So this is basically the state. This is the next state and this is the reward. So action is kind of hidden. Maybe you can think like that every from every state we only have one action and we are moving according to it. So estimate the state value function using first visit Monte Carlo evaluation. So this is the question. Like first visit basically means suppose you So in one episode you saw P is like P is the state. Then whatever like next comes, that's summation. Like since like here we have been given that it's this like it's not discounted, so gamma equal to 1. Otherwise we will have to use some these gamma powers also. So basically like for P we can calculate for episode 1. So this you need to take care of. So P like sum will be plus 3 plus 2 5, 5 minus 4 1, 1 plus 4 5, 5 minus 3 2. So this will be the sum. I'm doing this because gamma equal to 1. Otherwise, like if gamma was not 1, maybe zero point 0.9, then you'll have to add 0 0.9, then 0 0.9 square, like multiply minus 4 by this and then sum. But since we are given undiscounted MDP, this is given to like ease our calculation only. In reality, this usually doesn't happen gamma equal to 1. Because gamma equal to 1, it might happen if we have a finite horizon problem. But if we have an infinite horizon problem, then gamma needs to be less than 1. Otherwise, like there are issues like some things don't converge. So this is for episode 1. Now we calculate for second episode also. P. This is the first visit of P. So plus 3 minus 3. So we get 0. But these are two episodes. So you will like kind of oh no, it was not 3, right? 3 plus 2, 5, 5 minus 4. 1, 1 plus 4, 5 minus 3 equals 2. So 2 divided by 2. So the value of P, because there are two episodes, right? For every episode, there will be one value and 2 you divide it. So value of P is 1, right? Now, in a similar manner, you can calculate for Q. So what is the like first visit of Q? First visit of Q is minus from here. So from here, you can start calculating minus 4 plus 4, 0. Basically, it's minus 3 for first episode. This is for Q. And for second episode, like you start from here and calculate this. So minus 2 plus 3, it's like basically these three cancel. So it's minus 2, right? So since there are two episodes, so you average it 5 by 2. So value of Q is equals to minus 5 by 2. What is the option? Option C, right? Is there any doubt in this? Like this is first visit. Like what happens if like you have been asked to calculate the state value function using second visit? Then you will maybe for P you will start from this second visit and Q you will start from here. And in similar manner you can do for other episodes also. So is it clear like this one? So option C is the correct answer for first visit Monte Carlo. Now I'll check chat once I think something is there. How Q becomes minus 3. Okay, so I'll explain this again. So for Q, like for first episode, see, you have like first visit of Q from here, right? Then you calculate from that point because like what is value function, right? Value function is like for some state, like you start from that state and you calculate that summation discount return. Maybe here it's not discounted, but that return is there. And given that as t is equals to starting state is this. So this is our starting state and we are given first visit. So first visit of Q is here. Then minus 4 plus 4 is minus 1. Okay, okay. Did I make a mistake? No, no, it's correct. Minus 3 only. So minus 4, these two is 0 and minus 3. Yeah, it's minus 3 only. I hope you got this. Yeah, okay. Then I'll move to next question. So, okay, so we are given that considering the same transition data. So this is the continuation of this question only. Estimate the state value function using the every visit. Okay, so they are asking about every visit. So every visit you need to be careful. You need to track in every episode how many times we are visiting. So P is getting visited once, twice, thrice here. So there will be three values of P. Like one corresponding to the entire trajectory. Then second one will be starting from here and going till the end. Then third one will be starting from here until the end. And in a similar manner, like in second episode, there is only one. So we will start from here and go till the end. So this is how you will calculate. But since there will be four values, so when you are taking average, you need to divide by 4. So let's do for P first. So maybe I'll write this data here again, or maybe I'll refer it. So first P. So we are doing for episode 1. Okay, then so first visit value we have already calculated, right? So for P, what was it? 2. So 2, we got one value. And for second visit, we will get 2, like -2, then +4 +2, +2 and -3. So -1, right? So we got -1. And third visit, after third visit, so in every visit, like basically you have to count for every visit. So after third visit, we will get +4 -3. So it will be like +1. And for second episode, I think like there is only one visit and we already have the value. It was 0. So now when you are taking the average, so you have four like values and you need to do the average with respect to 4. So this will get cancelled 2 by 4. So value of P is 1 by 2. Although like you can see the answer from here, like this is the only one with 1 by 2. But let's calculate for Q also so that you get a practice. So Q. Okay. So for Q, first visit, I think we already have this value where it was -3. -3. Okay. Then second visit, like again, like we are just getting -3. So this is for episode 1. Now let's do for episode 2. Again, like first visit, we have the value, it was -2. And for second visit, again, like it's -3 only. So again, like you can sum them up and divide by 4. So it will be -11 by 4. And was it -11 by 4? Yes. So C is indeed the correct answer. So I hope you got this, like this concept of first visit, every visit, second visit, sometimes even if like longer data is given, like maybe some transitions might be even longer. So you might be asked third visit also. If you are asked every visit, then you need to factor in all visits, whether they are fourth, fifth visit, everything. And take special care when taking these averages. You don't have to divide by the number of episodes in every visit, but by the number of times you are actually having these values. So it's 4. So some episodes might be having more than one visits. Okay, so again, like the continuation of the same question. So in this question, now they are asking construct a Markov model. So basically Markov model is an MDP that best explains the observations given in question 7. Okay, so question 7 was basically this question only. In this model, what is the probability of transitioning from state P to itself? What is the expected reward received on transitioning from state Q to state P? Okay, so basically like they are asking, we have to either reconstruct the whole entire MDP. So let's do this. So let's see for transition P to P. Okay, so how many times we are moving from P to P? So when we are moving from P to P, like this time, then P to Q it's there, then P to Q again, here also. We are moving only one time, right? And the reward we are getting is 3. Now let's do for P to Q. P to Q, okay. So P to Q, like here, this is 1. So P to Q, we are getting reward of +2. Then P2Q here also +4, +2, +4. And again here also we are moving P2Q. So +2, +4, +3. These three we are getting. So +2, +4, and +3, right? So these three are the rewards. So basically either way, like we need to take average. So 2 + 4, 6, 6 + 3, 9, 9, 9 by 3 because it's 3 times. So we will get 3 only. Now what we need to do is Q to P now. Let's see how many times we are moving from Q to P. So Q to P once, like we got -4, and Q to P this time also, so -2. So we are getting -4 and -2. Again, like we need to take the average, so it will be -3. Now Q to Q. Let's see Q to Q. So Q to Q. This is Q to P. Okay. Q to P again. So we are not moving from Q to P any of the time. But like you need to remember one thing. Like at the end of the transition, there will always be a state which is known as the terminal state. So we need to factor in that also. So these transitions in like these two episodes is just like that Q from Q we are ending, but it might be possible that in some episode it might be you might be ending from P also. So you need to take care of these transitions also. So there are two transitions from Q to terminal state, and both of them are given reward of -3. So even though Q to Q there is nothing, so Q to terminal state we were getting 2 and both were -3 and -3. And similar manner, you can write P2 terminal state, there was none, right? So this is the basic reward. So we have the reward, like average reward, but we also need to have the transition probability to construct the matrix, right? So what is the transition probability? So if we are in state P, one time we are moving to state P and remaining 3 times we are moving to state Q. So this probability will be 1 by 4 and this probability will be 3 by 4, right? And Q to P, like we are moving 2 times and Q to T, we are moving 2 times. So half for each. So now let's construct the MDP. So we have a state P, we have a state Q, we have a terminal state. So the special thing about terminal state is that you can go inside the terminal state, but you will never come out of the terminal state. So when you reach a terminal state, your episode ends. You will need to start over from some new start state. So this is the concept of terminal state. So we now simply have to plug in the values. So P2P is 1 by 4 probability and reward is +3. So P2P will be a self loop 1 by 4 and +3. And P2Q is +3 reward and 3 by 4 probability. 3 by 4 probability and +3 reward. So Q to Q, we already saw there was nothing, but Q to P, there was something, and the probability was half for both. And even for terminal state, it was half. Now let's see the reward. Q to P, it was -3. Q to T also, it was -3. Okay, so this average will also be -3, then. So -3, -3. So this is the MDP, which we were asked to construct. Now, on the basis of this MDP, we need to answer some questions. So what is the probability of transitioning from state P to itself? So state P to itself, and they are asking the transition probability. So what was that? Uh, Wait a minute. What are they? What is the probability of transitioning from state P to itself? Okay, P to itself is 1 by 4. So these two are wrong. 1 by 4. And what is the expected reward received on transitioning from state Q to state P? So state Q to state P is -3, right? So we get -4. This one, 1 by 4 and -3, right? And did everyone get this? So they have asked P to P. You can see from MDP also, probability is 1 by 4. And here they are asking expected reward from Q to P. And Q to P is -3. So 1 by 4 and -3. This is the answer. So I hope you got this. If, maybe I'll check chat once. Yeah, okay, fine. Okay, so maybe like I think we'll move to the next question. So this is the last question in this segment. So again, like it's based on the same data. What would be the value function estimate if batch TD0 were applied to the above transaction data? Transaction, this like this is something. It's transition in RL. Transaction is in something in database. Okay, so transition data. And they are asking basically like we are giving those transitions, right? 2 episodes. So we have to apply that TD update formula, TD0 update formula, and see like what are the value we converge to. So let's do this. So what is our like equation? Like so one there are two ways of doing this. First option is Like you can either start with some value estimates of both the states and keep on like applying these TD updates. But that would be good if we are doing using a machine, right? Using a computer. Because we don't know how long it will take to actually converge, right? Convergence might be in terms of like when like suppose these two values, we will be updating it. So suppose if it becomes 1 1 in next step, then how long like it might take some time to converge. So instead of doing that way, we will opt for the second method. And like we already have the MDP, right? So from the statements, we have already seen like with finite data or infinite data, TD0 converges to Markov model, right? So now since we have formulated this MDP, we can simply solve this MDP, and we know like after applying these TD updates also it will converge to this Markov model. So we can simply solve this Markov model and get the answer of both the states. So let's do this. And how to solve this Markov model? Like simply we will use what is known as Bellman equations. Right? So let's do this Bellman equation. So maybe like I'll start for P, or maybe I'll move to next slide. Value of P. So what is this? Like first we will have transition probability, right? So from P, we were moving to P with 1/4 probability, and we were moving to Q with 3/4 probability. So 1/4 plus 3/4. This is the like summation, right? Over transition probability to the next state. So these two are the next states. There is a terminal state also, but you can write like 0 plus 0 multiplied by whatever. What was inside? Inside was the one step reward first. So what is the one step reward in 1/4 is plus 3. And again, in this also it's plus 3, right? 3 plus 3 plus. Now there used to be a gamma, but gamma since we are given 1, so we won't use that gamma. Now what we need is in this we were transitioning to P state only. So we will plug value of P itself, and in this we were transitioning to Q. So we will plug value of Q. So now this is our like equation number 1. Now let's see equation number 2 for Q. So this is the MDP. So for Q, like with half probability and both like we were moving to like we are getting -3 in both. But here like important thing to notice like value of terminal state is 0. Because what is value? If you start from some state, and what is the expected long-term reward you get if you start from that state? But no, none of the transition is going out of the terminal state. So you will get nothing out of terminal state. So value of terminal state is always 0. This you need to keep in mind. So now let's write the equation for Q. So we already know that the transition probabilities were half in both the case, and the reward was also -3, right? In both the cases, -3. And discount factor we have 1. But here, like since we were moving to that terminal state, so we will plug in the value of terminal state, which is 0. But here we are moving to P, so we will plug in value of P. So these are like two equations. So two equation, two variable, you can solve them. So let's do this. So first equation, what will it become? 4. Let's go there. Maybe I'll denote this just by P. So 4P is equals to this 3 plus 339, so 12, and there will be P again, and there will be 3Q, right? So this P, so implies P is equals to 12 plus Q, and this will become P is equals to 4. This was 3Q, so 4 plus Q. So is everyone agreed with this? This is the first equation. P, so basically you can write like P minus Q is equals to 4. Equation 1. In similar manner, you can solve this. So 2Q is equals to, this will be -3, so -6 plus P. So you can take this here. So P minus 2Q is equals to 6, right? So P minus 2Q is equals to 6, right? So you can simply subtract this. it will become q is equals to -2. So value of q is -2. You can plug it maybe in this equation. So -2, so it becomes p value will be 2. So 2 comma -2. So where is the option 2 comma -2? This is the option. So here, like, if you can, like, if you want to try, you can try this method also. You can start with some initial values of maybe 0 0 of both the states and keep on applying TD updates. But as a human being, like, it might take many iterations to converge. So we already know that what it will converge to. It will converge to that Markov model, and we simply use that data to solve this. So you need to be like careful with these also. Okay, so I hope it's clear. Is there any doubt in this? Because this is the like last question of this segment. And after this, I'll move to demo. Okay, so it's clear now. I'll move to demo. This demo is related to Q learning. Maybe I'll share the Mozilla. Okay, so can someone confirm? Are you able to see browser? Yes. Okay. Okay, then I'll see this. So basically, like today's demo is regarding Q learning and SAS. So maybe I'll describe the problem first. So the problem is the same one which we have already uh, discussed in class. So it's called Cliff World. I'll take that. So there is this grid. You can think like, so we actually saw an example of this in class also. So these are the, like, you can think like these are the cliff. Like if you fall into this cliff, then you get a reward of -100. And this is our start state and this is our goal state. So we need to start from here and reach this goal state. And we also saw like two methods, how those Q learning and SASA were performing. Q learning was learning like this, and SASA was preferring a safer policy, right? So this is the environment which we are considering, and for that, like, we'll see demos of Q learning and SASA. I hope like the problem is clear to everyone. So I think like there is a question in assignment on the same problem also. So now I'll like start this. So again, like these are the parameters, like start state is bottom left. So yeah, one thing to note is like although like I have drawn a grid of different size, so size may vary, but the concept is like there will be in the last row there will be one cell, like, and the bottom left one will be the start state and the bottom right one will be the goal state, and whatever in between is there in the last row, it will be the cliff. We need to avoid cliff. Also, one point to note is like for all other transitions we were getting a reward of -1. So there is a reason why this -1 is used, because -1 kind of enforces the agent to move to the goal state as quickly as possible. So if we are using -1 kind of reward, then we can use our discount factor as 1 also. If we were not using -1, if we were using some positive kind of reward, then we will actually need this gamma to be less than 1. Then it will kind of enforce that you need to reach the goal state as soon as possible, and you can have a like very bigger reward, maybe +1000 for reaching the goal state. Because that way, like the agent will like try to reach as fast as possible so that this effect of gamma square, gamma cube, if you reach later, you are basically diluting your reward, final reward. So that kind of ensures the sense of urgency. So again, like maybe I'll run this. While running, I'll explain this. So the start is state is the bottom left, goal state is the bottom right, and the cliff is bottom row between start state and goal state. So we have 4 actions. Again, no diagonal movement. So you either move up, down, or left, right. And you also need to ensure that you don't fall off from the cliff, right? If you are in the uppermost row and you are like trying to move up, then you will stay in that only. So that thing is also coded here. So, and the rewards are the same. So basically, like we have like used this encoding 0 for up, 1 for down, 2 for left, and 3 for right. So these are the encodings which we have used to represent the F4 actions. And -100 for falling into the cliff, otherwise -1 for all other transitions. So again, these are the import statements. We are not using some environment, right? So there is simply NumPy, random. This is matplotlib for plotting. This is C1. C1 is also like it is used to generate high quality plots. Matplotlib like it generates basic plots. So if you want like to generate quick plots, then you can prefer matplotlib. But if you want like if you are willing to spend time and you want quality plots, then it's better you go for C1. And this TQDM is simply to display the progress bar of our training. And pretty table is like for printing a table in a like very pretty manner. And in similar manner, we are using this default 10TQ. So what are the parameters? So I mentioned that cliff can be of different size. So here like we have considered the width. So basically like this, you remember. So basically the number of cells in a row is 12. So this is the width and this is the height, and cliff height is 4. So 4 rows, 12 columns. So this is our like grid and starting point. So like in computer science, like this matrix starts from zero indexing, right? So first cell will be 0, comma 0. So since we are like maybe I'll write a different one. So first cell is generally 0, comma 0, then 0, comma 1, then 0, comma 2. No, this is like zeroth row. First index is for row, so 0, comma 1. And in similar manner, you can go down 1, comma 0, 2, comma 0, and 3, comma 0. So first one is the row index, and second one is the column index. So this is our start state because since our grade is of 4 rows and 12 columns, so we start from 0, 0, 1, 2, 3. So this is our start, and this is our goal. This we have specified here. Hmm, just a minute. Yeah. So endpoint again third row and the 11th because bottom right, since we are having two like 12 cells and starting from 0, so 11th will be the our goal endpoint. We are representing that by endpoint. This is the start point, and again the same encoding for actions, and these are the like our parameters. So I but you can tweak around with these parameters. There might be some more modifications you might need to do if you like change these cliff kind of parameters, environment variables, because like I have something hard coded here. So epsilon is the exploration factor. So like epsilon degree is the exploration strategy which is getting used. So 10% of the times we will take exploratory action, and alpha you remember that in TD update equation there was that alpha which I was referring to as learning rate. So it's 0.5 here. And gamma is the usual response factor. Since we are using negative rewards, so we can take gamma equal to 1. Negative rewards will like kind of ensure that sense of urgency in the agent. So there are some functions which you need not to worry about for plotting and all. I'll simply explain what is the main concept here. So this is the function for getting next state from the current state and action taken. So there is a next state function. You simply supply what is the current state, what is the action you are taking, and it will kind of ensure like it will return you the next state, right? And also the reward. So this is function is acting as the environment. Also like here I have used like max and min. This kind of ensure that the agent does not move outside the grid. So if you are in the like you up topmost row and you are taking up action, then you should not go fall off the grid. So this ensures this. And in a similar manner, like this functionality ensures that if you fall in the cliff, then you get reward of -100. So, and like the episode ends and you start over again because next state now goes to start point. So since we are having this fixed starting state, so we are always moving to that start point. If we were not ever having a fixed starting state, then we could have started anywhere in any of the cell. And the goal state will remain fixed. or you can do some tweaks, like you can have start state somewhere, goal state somewhere. So that kind of changes you can try out. So this is also a function to extract optimal policy from Q table. So there's nothing much happening here, simply argmax. You know how to extract the policy from the Q table. Just take argmax over all the actions and it will come out. So this is the utility function to find path using optimal policy. So this is simply for printing purpose. So once we have the optimal policy, then optimal policy will simply specify if you are in this state, then should you go up or right or left or down. So on the basis of that, for plotting the actual path which we followed, we had this function and utility function to display optimal policy also. So these are just for displaying. So this is the epsilon greedy policy which we have used. So you can see like if we are basically generating a random number here, it's between 0 and 1. If it's less than or equal to epsilon, so our epsilon is 0.1, then we will take a random choice of action. Otherwise, like we will simply do the greedy choice, which is taking the argmax over all the actions. So here you are seeing two state components because our state comprises of two coordinates, right? X coordinate and Y coordinate. So now let's move to first implementation, which is SASA. So this is the SASA algorithm. So this image is from Satin and Barto book only. So I hope there is no doubt till now. If there is, you can maybe write in chat or unmute and ask. Otherwise, I'll move to the SASA. Okay, then I'll move to SASA. So this is the basic SASA algorithm. So you are, this is the complete loop. So we have already done this above, like step size. Some people call it step size alpha. I call it learning rate. And this is epsilon is the exploration factor. This we have already done. And you can initialize also. So we are using zero initialization as I'll show you later. And this is looping. And they are using the terminal condition in the end, but you can put it in the beginning also. So in this loop, until you reach the terminal state. So this is for one episode. So you at the in each loop, like for one episode, what you will be doing, you will initialize the start state. So here our start state is fixed. We don't need to initialize the start state. We always have to start from the same start state, which is the bottom left. So this we can avoid, but we can initialize it if you want to try from different start states. Then we are choosing the action A according to the epsilon greedy policy. This we have already seen here. So this according to this epsilon greedy policy, we will supply the state and the Q table, current Q table. And then on the basis of that, it will either return an exploratory action or a greedy action. So with 0.1 probability, it will return a exploratory 0.9 probability, it will return a greedy action. So greedy action basically means whichever action for that state has the highest value. So it will simply, it is doing this argmax. So this component colon here, so it kind of, it is taking this argmax over this action. So third component is action. And our state is like two components because x coordinate is 0 and second is y coordinate. Now, once we have taken that action A, now we are looping for each step of the episode. So this is like for that transition. I showed you like one transition is like state, action, reward, and next state. So this is like for that each step of the episode. You take action A, you took action A, and then observe reward R and S dash. So basically, like you have the state, you can take the action, then this will go to this function, right? Where was this function to get the next state. So you supply the state and action, and this will return you the next state and the reward. So this you will get here. Now you have observed this reward and the next state. Now you can choose action A dash from this new state because you know SASA is on policy. So if something is on policy, you need to know what is happening in this next state also. You know, like this SASA name is derived for state, action, rewards, next state, and also the next action. So this is like quintuple, tuple of 5 components. So it uses 5 tuple information. So this we are using it and we are getting the next action also alongside next state, and this also we are getting from this epsilon. It's just that here like we are passing the current state s dash and the action a dash. So we have gotten this action a dash, once we have all the like components, we can simply plug in this update equation of salsa. So since it's on policy, like this is the update equation, this is the new estimate. Like in computer science, you can do like you can reuse the same variable. So it will simply kind of update in the same variable. So this is the old estimate plus learning rate time, whatever reward you got plus gamma times, gamma is 1 here. And this is the like this complete thing R plus gamma times. And this is the like estimate of the next state. This is called bootstrapping. So we are using that bootstrapping and this is subtracting the old estimate. So basically the new estimate is equals to current estimate plus alpha times this TD error. And then since you need to move to the next transition, so you will current state, you will initialize this to next state and current action to next action. So now this loop will start over again. And this will keep on happening until like we reach the end of the episode. So when end of the episode happens, like we can do this entire procedure for the next episode. And we can do so in this problem like we have done for 500 episodes, but you can decide like how many episodes you want to do. So basically more number of episodes means better information. Like there is less stochasticity, so everything like kind of averages out. So it's better like whatever number of episodes you can afford in your computation power, you can do that. So this is the sasa algorithm. So similarly, like the same algorithm has been coded here. There are some extra components also. Like this is simply for the purpose of plotting of graph. So we are maintaining a total reward variable and like updating it also. So here, like you can see the similar thing is happening. So start state, we are initializing. So this is like we are not looping over every episode because there is this second thing. It is actually looping over that episode. So what is happening here is like Q table. So we have here initialized it with 0. So these are the like our height and width. So our number of states will be basically 4 into 12, right? And for each of those, like there will be 4 actions. So this is our like 3-dimensional matrix, of which like 2 of the components are corresponding to state and 1 component corresponds to action. Or you could have had like just a 2D matrix also, but then you will have to club like you'll have how many states? Either way, like the number of states will remain 4 into 12 only. So this I have used that 3D matrix, but you can use a 2D matrix also, but you will have to make changes accordingly. And like here also one more concept is like since this is a stochastic method, so every run of salsa might give different result on every run. So we are like doing multiple ones and taking the average for the purpose of concluding something from it, driving some conclusion. Now we are like in doing for all episodes, we are getting calling this function and getting the reward. So this is returning the total reward of that episode, and we are calculating the average reward on every run. And now this is the same salsa algorithm which is happening here. So this is like for every episode, this function is getting called. And similar kind of thing, you are getting next state and reward from this next state function. Then okay, what is the role of TQDM here? So TQDM, I'll show you later. Like TQDM helps in printing the progress, like on what episode we are, and like it kind of gives you. I'll show you maybe. So this progress bar, 100%, like this keeps on increasing and you can see how much progress you have made. So it helps like sometimes you are simply waiting. Instead, like you can see a number that it's 50% done or something. So that is ensured by TQT. Oh yeah, I hope you got this. Yeah, okay, so I'll move. Range, yeah. So range is like number of runs. So later I'll show you like this is the number of episodes, 500, and we are averaging over 50 runs because one of 500 episode might give some result, but second one might give another result. So we are averaging over 50 runs so that we get some, we can conclude something out of it. You know, like the central limit theorem, if there are stochastic processes, then you can average over multiple times so that like you can get some conclusion. Otherwise, like these episodes, like you don't know how they are getting generated. There is a lot of stochasticity here. So in order to average out that, like we are doing multiple runs of this salsa. So you can think like this salsa algorithm I am running like 50 times and taking the average over that. Okay, so I hope you got this. So now I'll move. So this is the like SASA algorithm. And in this, like while like we have not reached the terminal state, so they had this condition in the end, we have in the beginning, we are doing this next state, and using next state, we are kind of getting. So let's start from the initial point. We already have these. So initialize as this we have done, and then we are getting this action from the epsilon greedy policy, and then we are looping this till the terminal state, and we are getting this next state and reward from, by taking this action. So and then this step choose action a dash. Now we are passing the next state and to get the next action. So we are getting a dash by passing s dash. So s dash is the next state. And this we are doing for the in an epsilon degree manner. Again, like this statement totally what this is simply for plotting purpose. We will see the plots afterwards. Now we are like in the region where we need to calculate this update. So we do it in step-by-step manner. First, we will calculate the target. So target is reward plus discount factor, which is gamma, plus Q value of next state and next action. This is there. Okay, so this is the target which we have calculated. Now, after target you have calculated, you need to find the current also. Right, current you can simply obtain from the Q table. It's already stored in the Q table. You just have to like go there and find that index. So we are simply passing the current state, which is a state. See here, we are passing the next state. Here we are passing simply the state and the current action also. Here we are passing next action. So it's SND. So we have the current estimate also. Now we are doing this update. So what is the update? Update is basically this entity, like whatever is after the plus. So we have simply multiplied this alpha into this is the target minus current. So this is the update which we will be doing. And this is the index where we will be updating, right? Q of SA. So this is the state action and plus equal basically means equal to this entity plus you are adding this. So this is a computer science construct programming language. You might have seen it in C, C++ also. So this is basically updating the Q table. And again, like this thing S, you are supplying like next state into the state and then next action into the action. So in this way, like we have done this and this will like return the total reward. And then like this is like kind of looping over episodes and runs. And in this way, like this thing is SASA is happening. And in a similar manner, it's Q learning. So I hope like there is no doubt with respect to SASA. If there is, you can ask me now. So like SASA is the second most popular algorithm, and after that, like first most is Q learning. So like in planning, like there is policy iteration and value iteration, and in learning, you can say if you are doing model free learning, then Q learning and SASA are very important. There is one more method called model based learning, which will come later. But in model free, like these are the two most popular algorithms. Okay, then I'll move to Q learning. So okay, yeah, welcome. So Q learning is like, again, like I think I forgot to mention, this is SASA is on policy, you already know it. And this is Q learning is off policy. So some differences here, like the same ones as discussed in the class, like here we have already initialized this step size, basically learning rate, we have 0.5, epsilon is the exploration factor 0.1 here. Gamma we are taking as 1. Again, like similar to SASA, we have initialized as like 0. And the start state, like all this is terminal, all this is initialized as 0. Maybe I'll show for SASA here. So this np.0 is like is kind of doing this 0 initialization. Now in Q learning, what you are doing, this is for one episode. For each episode, you are like initializing the start state, which is same for us. And for each episode, we are taking the action A from this state based on some epsilon greedy policy. We have already seen the epsilon greedy function. Then see here, like we never use A dash, right? In SASA, we were using A dash. So this makes SASA like Q learning off policy because we don't need the next action also. So this is how it works. So take action A, observe, reward, R, and next state. This we can get from that function which we already have. Since we have the state, we have the action, we can pass them and get the reward and next state. And then we can update this. So basically here we are taking just max. So similar kind of update here. Just that here, like instead of having the on policy update, which was using A dash, but here we are using whatever is the max over all the action. And then the same thing S to S dash. Now remember, like there was A to A dash here. Here it's not needed in Q learning because we are doing off policy. And this we do until the termination, which is either we reach a goal state or we fall into the cliff, then the episode will end. So similar thing is coded up here. Start is equals to start point and then loop for each episode. So this reward is simply for plotting purpose. We will see the plots later. And then we are sampling this section using excellent greedy policy. We have passed the state S, and then like we are taking this action and state and getting the next state and reward one, and this reward total reward plus equal to is simply for plotting the graph. Then now we are into the zone of this update equation. So we have already done these two steps, right? Observe the reward and the next state. Now we, again similar to SASA, we calculate the target. So target equals to reward plus gamma times. So remember here we actually need the max. So we need the value, not the argmax. Argmax gives us the action. Max will give the actual max value. So we need that. So we do this. So this is the target reward plus discount factor times max over all the Q. They will like basically max is over all the actions. So this is the target which we got, and current we can simply get by reaching the index. So you pass the current state and current action, you will get the current value, current estimate of this queue. And again, like this is the update alpha multiplied by this TD error, target minus current. Okay, I'll check once. Okay, yeah. So this is the thing, and then like you are updating this. So this is again plus equal to this update, and then state equals to next state and returning the total reward. Again similar to SASA, same thing is happening here, like you are initializing with 0, then like doing multiple ones, many episodes, and calling this again and again. So now I'll show you like the actual function. So there's not much happening here. This is just getting called again and again, and the number of episodes is 500 and the runs is 50. So now it's already around 7:30. Maybe I'll show you the actual thing. So see, this I have already run in the beginning, so it has run by now. So this progress has happened. So first one corresponds to SASA, second one corresponds to Q learning. So what is the Q learning policy? You can see here. So this is our start state, right? So start state, when you go up, so Q learning is saying that you go right, and come down. So this is your goal state. But whereas SASA is kind of saying that, so maybe you can see better in case of this path. So Q learning is saying that you do this path, which we have already seen in the class, like closer to the cliff, but the shortest path. Whereas Sasa is preferring a little safer route. So here, like it basically depends on the episodes how you have sampled. There are, if you run this again, maybe I'll run it again. Sasa might like take the even more safer path, like it goes to the extreme. Even in these two, it goes here. So it basically depends on the episode. So since I am using 500 episodes, it converges like this. If in another 500, it would converge to the exact like safer route. So maybe I'll show you once more. Let's see if we are lucky, like it might happen. Otherwise, like you can simply increase the number of episodes and see. So it doesn't take much time. Over here, it converts to even worse one. So okay, that's fine, but you can increase the episode. But the thing is, like Q learning, it's definitely converging to the shortest path. So this is the like average reward. So number of epochs. So you can see like around 20 less than, it is like taking around 20 steps, but it should be taking how many, like 12. So on an average, like it's flipping around. Maybe sometimes it's taking 16 here, sometimes it's taking around 20. Even in the beginning, like it's taking much, but gradually it's improving. So this is over the like number of epochs. So this is kind of average. So this is why we were using like 50 runs. So even after 50 runs, you can see like there is a lot of stochasticity. We couldn't get a smooth kind of graph. So maybe you can increase the number of runs also to maybe 1,000 or something, then you can get a smoother graph. And then this is the value function, which as usual as expected, like will be zero for all the terminal states. This is the cliff. Also like goal state is a terminal state also. And similar manner, like as close, since all our rewards are negative, so all the values are negative, but as we get closer, it's less negative. So yeah, I will be sharing this. So basically, like in the Excel sheet, like there is a Google Drive folder also in which slides and quotes and even like some other material are is shared. So you can play around with this. So another thing is like this. So what we have done is what is happening here is epsilon we already had 0.1, right? Alpha we had 0.5, but here we have kind of decreased the learning rate to 0 from 0.5 to 0.1. So basically like decreasing the learning rate slows down things because you have to do more number of updates to get there, and gamma as usual is 1, so you can run this maybe it's already run there. So here you can see like it took 14 seconds something, and it took 15. So here we can see like in 1 second we are able to do 15 iterations and 9 iterations, so more iterations in like if we use the learning rate of 0.5. But here we are becoming slower, right? Slower in the sense like we are doing less number of iterations in the same time, 1 second. So this is slower. So in similar way, like you can play around with these parameters and see how it works. I have some more like you can change these, and some further experiments will be like you can try different values of epsilon, alpha, and gamma. Decay. So here, like we have used the constant alpha and constant epsilon. So you can decay epsilon and alpha, like, and maybe you need to follow those conditions. You remember, like summation should be tending to infinity, but summation of squares of these values should be like should be less than infinity, some finite value. So as long as those conditions are uh, there, then you can use the decay. You can try out that. You can try out different reward formulations also. Here, like we have negative reward like -1 for each transition and -100 for falling into the cliff. So, but you can try out, maybe you can give +100 for the goal state. Then you can introduce discount factor. Here, like we have one discount factor. Then you can introduce 0.9 discount factor or even 0.5. And then the agent will have some urgency to reach the goal state as quickly as possible. And then you can do more training. So as we saw in case of Sasa, right, it was taking a safer route, but not the most safe one. So you can increase the episodes and see like how it performs. Maybe it will like take even the most safer route. And you can increase the number of runs also so that those graphs become smooth. And so this is like only Sasa and Q learning. You can try expected Sasa on your own, and you can even tweak the environment, right? Be careful with it. Some like hard-coded things might not function, so you need to change those also. So you can like I showed you like these things in the beginning. Cliff width, you can play around with cliff width, cliff height, and starting point, end point. But make sure like the other parts also get updated. Okay, so I think like this was the entire demo. It took almost half an hour. So if there is any doubt, you can ask me now. Otherwise, like I'll move to the last segment, which is the assignment. So I'll download this. Okay, so also like last week, like in week 6, you can try out not just I demonstrated Q learning Sasa. You can try out like how these DP, Monte Carlo, and TD methods for the purpose of evaluation. So this is control, right? TD control. Q-learning and Sasa are TD control method. You can try out for policy evaluation, Monte Carlo methods, and TD methods, and dynamic programming, and see like how they perform. So all that you can do, because like we have limited time of 2 hours, so I can cover this much only. And again, like next week, we will be moving to TD lambda. If there is not much, then maybe I can show something about Monte Carlo and TD and DP. Okay, so then like I'll move 2 slides. Okay, so maybe someone can confirm if you are able to see the slides now. Demo is done. Assignment 6 now. Okay. On 23rd Feb, I had posted question in forum regarding some evaluation done for question 4 of assignment, but I am still to get clarity on that. Okay, so forum actually forum is not being managed by us. So I'll see if there is something which can be done on there. So let's move to the assignment 6. So this week we have assignment questions on TD, then TD0 basically like 10 TD control like Q learning, SASA. After state there might be one question. Before that we had UCT and of policy Monte Carlo. So in this segment, as usual, I won't be giving you the exact answers, but I'll guide you through to the answers. So let's start. So first question is, in order to use importance sampling for off policy Monte Carlo policy evaluation. So this is what I was talking about. So control we have done, but policy evaluation you can try out both. So in order to use importance sampling for off policy Monte Carlo policy evaluation, we require knowledge of state transition probabilities of the MDP. So is it true that we are doing off policy Monte Carlo? We are simply generating trajectories. Do we actually need the state transition probabilities? How this is happening? Because we were generating the trajectories, which need not, we were not requiring the information of transition probability. In Monte Carlo methods, were we actually using the transition probabilities anywhere? No, we were not using. We were simply generating trajectories and maybe taking the average over them and see which action performed the best. So this statement is wrong, right? We don't require the knowledge of transition probabilities. So even if you have a in Monte Carlo methods, we know if you just have a simulation model, you can generate trajectories from that simulation model, take the average, and see what is the best action. So that transition probability is not needed. Maybe you can consider the name of chess. So in chess, you don't need the probabilities like these complex programs like AlphaGo and whatever, some are used for playing chess also. So they don't require the knowledge of transition probabilities that if you are in some state, as maybe a state here comprises of the board position, like one snapshot of the board. So what is the probability that I maybe if some pieces were in this manner, maybe one of the pieces will move here. Do we actually use those transition probabilities? We don't use in Monte Carlo method. So this statement is straightforward wrong. So assertion is wrong. So we can rule out first two option. So again, but I won't give you the answer, but reason you can you need to uh, understand whether it's true or false. So assertion is okay. So if assertion is true, then definitely. Uh, Russian is true. Okay, this is not there. Okay, so these two are still possible. Reason could be true or false. So we require knowledge of the probability of each trajectory according to the estimation policy and according to the behavior policy. Do we really need, so what this is taking, suppose if our estimation policy is pi and our policy this is mu, both of these values are dependent on the state transition probabilities of the MDP. Do we really require this? So we are using importance sampling here. This is the important thing. So important sampling, suppose if we denote this estimation probability by P, suppose this trajectory is xi, we were not, we don't actually need the actual values of these two, right? We simply need the ratio. And if you expand out these ratios, you would have seen those transition probabilities were actually getting cut. So maybe I'll write one equation here. So P of xi. So suppose this trajectory you start off with some state p of s0, then you will take some action e naught according to this state, then you will have some probability of transitioning from state maybe state s1 from s naught and e naught. And in a similar manner, you can have q xi. So basically, like you this for pi and this for mu. So what thing will change is like only this thing will become mu, and since we are interested in only the ratio, so this will get cut with here and this will get cut from here. So these transition probabilities are not really needed. But here the reason is saying that we require the knowledge of the probability of each trajectory. We don't. We simply need the knowledge of the ratio, not the transition probabilities, because the transition probabilities, if we expand this ratio, those get cut out. So we don't need that, right? So reason you can see like it's true or false. We don't need that information of transition probabilities in Monte Carlo method. Okay, then I'll move to the next one if there is no doubt. So again, multiple option correct. Which of the following are true? So this, I think you have seen the lecture. You can simply write it from there. So DP methods use full backups and bootstrapping. So DP method, dynamic programming, basically we use full backup because like we are calculating every possibility. We were summing over S dash and we were summing over all the actions, right? There was this and this transition probability. So we are using full backup, not just one backup. And bootstrapping also we were doing because like it was after transition probability, there was this reward term plus gamma times. Here we were bootstrapping, YV or Q, whatever. So this is correct. PD methods use sample backups and bootstrapping. So in TD methods, we were not using the full backup, right? We were not doing the summation over all possible state, next states and actions. We were simply doing one transition SAR and S dash. And on the basis of that, like it's sufficient to make the update. But we were doing bootstrapping also because like this target, if we were using suppose and one step target, then it's R plus gamma times. Here we were substituting that value of next state. So we were doing bootstrapping. So TD methods use sample backups. This is true. Now the question is Monte Carlo methods use sample backups and bootstrapping, and Monte Carlo methods use full backups and no bootstrapping. So do they use like so this use means always use, right? Do they always use sample backups and bootstrapping? Need not. Like if you have computation power, you can go till the terminal nodes, then you don't need bootstrapping, right? So this is wrong. And do they use like full backups or sample backups? They definitely use sample backups because like you are not doing like so. If we were using full backups on Monte Carlo, so we would have simulated all the possible trajectories, whatever is possible. But we don't usually do that. We sample some of them and take the average because that is feasible in our computation power. So in complex games like chess and Go, like this tree is so large that you cannot try out every trajectory and that too till the end. So whatever is feasible, we maybe sample some of the trajectories and go till certain depth only. And then we do the planning accordingly. So accordingly, you can get the answer. So I hope there is no doubt in this one. Okay, then I'll move to the third question. Okay, this is regarding UCT. So upper confidence trees. So which of the following is true? So this requires two statements. We typically require a simulation model for the environment. So what is like UCT? UCT is a planning algorithm, right? Because we need to generate those trajectories from some state. And for that, you need a simulation model. You cannot like generate those trajectories from real world model because real world model will like actually show you the actual path which was taken. It won't show you like what could have been possible if we took some other action. Whatever you took, it will show exactly one path if we are following real world model. But if we have a simulation model, you can try out like what would have happened if I would have done something different than what I have actually done. So simulation model we typically require. And it uses excellent greedy exploration for action selection. Does it use this epsilon greedy exploration? What does this UC mean? UC means upper confidence, which is based on UCB, right? In UCB, were we doing epsilon greedy kind of thing? No, right? Because UCB, there was a term, right? You remember 2 ln t upon maybe number of times that arm was sampled. So this term was ensuring exploration. And we also saw a demonstration. We also saw that demonstration of this UCB, how it was like beautifully doing this exploration and exploitation. We didn't have to intervene. It was doing it on its own, simply by like sharing the UCB values. So we do not need this this epsilon greedy exploration is not needed. It computes an upper confidence. Okay, so this they have given in next option. It computes an upper confidence found on the value of state action pairs. Yeah, definitely. So now the last question is it a variation of Monte Carlo research algorithm? So I won't give you this because this will determine the answer. But if you have seen the lecture, you know what like MCTS is the general algorithm. One of its variant is UCT, which uses upper confidence bound. There are other like UCV algorithms also like UCV similar to UCV, KLUCV. So you can find something like KLUCV trees or something else also. So there are different types of Monte Carlo research algorithms and UCT is one of them. Okay, so if there is any doubt, you can ask me. Otherwise, like I'll move to the next one. Okay, so again, like this is which of the following are true. So consider the following statements. TD0 methods use unbiased sample of the return. Is it like unbiased sample? So TD use like this kind of data, right? To make the update. It could be biased, right? If you are in some state and in some action, you are not like exploring every possible action. Otherwise, you would have done this sigma kind of, which DP does or overall the possible there will be some probability of action and overall. So we are not using the unbiased pattern. We are using a biased one because but the like since we are doing it again and again over a long number of like large number of times, it basically converges if we do till infinity. But as of now, like one update, like you cannot say that it's unbiased. So this is wrong. TD0 methods use a sample of the reward from the distribution of rewards. Yeah, like they use a sample of the reward, right? So one since one is wrong, this is ruled out. This is also ruled out. Uh, okay, so either way, like you can get the answer, but let's see the other options also. So this they definitely do. TD0 methods use the current estimate of the value function. So do they use the current estimate of the value function? Yeah, like so basically like current like some people write it as new and old. So old you can write sometimes as current. So it uses that current estimate because this is what we are actually updating. So we are using the current estimate to update. You remember that equation. V new is equals to left side V current plus alpha times TD error, which is also denoted by delta. So I think you got the answer in this one, but let's move to the next question. So if there is doubt, you can ask. So Q learning can use asynchronous samples from different policies to update Q values. So asynchronous basically means something which is not generated by the same policy, right? So we know that Q learning is off policy, right? So for off policy algorithms, we can actually do this, right? By and we can use some other new policy, behavior policies, estimation policies, something different. So we can use asynchronous samples. This is true. So yeah, this one is ruled out. So Q learning is an off policy learning algorithm. I think like like I have already mentioned like whether it's on SASA is on policy, right? Q learning is off policy. And is this is true definitely, but you need to see like is this the reason? Yeah, like it seems like this is the reason. They will like answer. Now let's move to next question. So suppose for a two-player game, we have modeled as an MDP. Instead of learning a policy over MDP directly, we separate Okay, deterministic. So this is the like after state lecture. Consider the following statements. So the following statements are the set of states that make up after states may be different from the original states set of states of the MDP. You remember this example of tic-tac-toe. Suppose we are the player that is playing first, and we will always encounter states. Suppose initially we will encounter empty one, then maybe like we play environment, the opponent will also play. We will encounter only those states in which there is equal number of noughts and zeros. But the opponent, which corresponds to after state. Suppose if we have played one move, then he will encounter this. So in this like number of, if we are using this knot, then it will encounter only those states in which number of knots is more than one more than the number of zeros. So if we opponent plays like this and we play like this, then this state will be supplied to that opponent. So this is its after state. The point is that set of states that make up after states may be different from the original set of states of them. We can call this original set as S and maybe after state as S dash, like the complete set. So that can be different. This is true. Now the second question is the set of after states could be smaller than the original set of states for MDP. Can it be? Like maybe I'll give you a hint. So there are cases where one state from S, suppose small s is this one state of this set and small s dash is one state from, so maybe index it y1, s2, s3, these are small. So many can map to the same after state. So it can be smaller. It can be smaller, right? Based on that, you can get the answer. Now I'll move to question 7. Okay, so this is actually the cliff-wise problem, which we have already seen the code also. It was demonstrated in lecture also, and I think it's in the book also. So this is like everywhere. So consider the environment below. Suppose we use epsilon greedy policy for exploration with epsilon 0.1. This is the same epsilon which we used also. Now we need to select the correct option. So okay, so this is simple lecture based. Like we have already seen the code also. So Q learning finds the optimal wet path. Yeah, this was for Q learning, right? And Sasa finds the safer path. So you can like get the answer right. Q learning finds the optimal wet path and Sasa finds safer blue path. So this like I have already marked the answers because you already know. We have already seen it in the code also, lectures also. So this is like simply question for those who have actually watched the lectures or even attended one of the sessions, they can simply do it. Now the question is, having a simulator or model is an advantage when using rollout-based methods. So rollout-based methods are MC methods basically. You can see rollout-based methods came before like these before these MCTS and all, but you can consider MC as one of the rollout type of method. So we are basically generating different trajectories, right? And having a simulation model helps us. That is true. Because we can, if we are using real world model, then we would only get the thing which is has actually happened. But suppose in 2002, maybe if we are considering trading agent to 2010, the prices went like this for some stock. So you will have that data only, but you don't know like maybe if it's for Apple, maybe if Apple took some decision which was different from the one it actually took, maybe it like did some merger acquisition in a different way than it actually did, then the prices might have moved in a different way. So we cannot do this kind of simulation with real world data only. So simulation model definitely helps. So that is cool. And the reason they have given is multiple trajectories can be sampled from the model from, yeah, like this is what we are actually doing. So this is also true. And you need to just simply argue whether it is the correct explanation or not. Okay, so if maybe I'll check the chat once if there is anything. If there's nothing. Okay, so like the assignment and even the practice assignment don't have many numerical questions, but I think this is the one. So consider an MDP with two states A and B. Given the single trajectory shown below, so we are given one episode. in pattern of SR. So again, action is missing here. You can think like there is only one action. Uses on policy TD0 updates to make estimates for the value of these two states. So there are two ways of doing this. I already mentioned the first way you can construct an MDP, but there we did that because we already had to construct the MDP in one of the previous question. But maybe here we can do it in actually update to it. So let's do this. Assume a discount factor, the gamma one, learning rate also one. So this they have given as one to ease the calculation and initial state values of zero. Okay. So what are the estimated values of two states at the end of the sample phase? You are not asked to compute the true values of the two states. Okay. So one more thing. If you do like that MDP kind of thing, it will give you the true value. But here, like we are given only one episode data. If we have like multiple episode data, then only we can converge to actual. So this might be different. So here they have explicitly mentioned that you don't need to like formulate that MDP and calculate the true values. You simply have to apply the TD updates starting from 00 for both states and see like what happens at the end of these episodes. So let's do this. So, and we have all the things given. Action we can take simply as one, right? So what is the TD update we can write? We knew state, I'll simply write as, it can be two states, A or B, right? So here we have two states. So we hold of as plus alpha. Alpha we have already given one. Plus whatever reward we can get it from here, reward plus gamma again like we have been given as 1 and what will come later, value of the next state. So this we can determine based on if we are moving from A, then here we next state will be B. So on the basis of that we can do this update. So let's start. So maybe I'll start on the next slide. So initially like we can do like VA, value of A is 0 and value of B is also 0 initially. So after first transition, let's see what happens at the end of first transition. So our update equation basically like if we simplify it basically becomes V new of state S is equals to V old of state S. This goes to 1 plus, so this also goes to 1 plus reward plus whatever next state. I'll write next state here. This is our update equation, right? So let's do this. Okay, so value of, wait a minute. Uh, we are starting from 0, right? Hmm. So old value of A will be 0 only, right? 0. So this we are doing for the first one is equals to 0 plus. So we are getting reward of 3, right? And 0 plus 3 plus value of next state, which will be B, but since its value is 0, so value of state A will become 3, right? So this you got it, value of state A will become 3. So now at the end of like first data point, we have this value. Now in a similar manner, you can do for value of state. Now you need to like do for B because now we are at state B. So state B will be, what was the value of like, what is the reward which we are getting? We are getting is 2. So this slide, there are two ways of doing it. One is asynchronous way and one is synchronous way. So synchronous way means that if you are doing, you like use this B equal to 0, or asynchronous way means like you have already updated the value of A. So this was, let's suppose at 0th step. If this is at first step, and you can either use this value or this value. So it answer will basically depend on whether you are doing it asynchronously or synchronously. So let's do it synchronously. So maybe like you can see like if our initial value of B was either way 0, so here it doesn't matter much. And the reward which we are getting from moving B to A is 2. And what is the value where we are moving? A. So we have initial value of B. This is like maybe like let's do asynchronously only, because like your is there anything mentioned in the answer? Okay, so by default it's asynchronous. We can use asynchronous because like either way, this is considered as first episode. This will be considered as second data point and then third and in this way. So let's do it asynchronously only. So 2 plus 3 because this is where we are transitioning and its sole value is 3. So value of B will become how much? 2 plus 3, 5. Now you need to keep this in mind that this is now the new value of A and this is now the new value of B. So now we have done this, we have done this. Now we are at A again. So let's do for A. So, so old value of A is 3, right? Plus, what is the reward which we are getting? 5. Okay. And what is the value of B? B is 5. So in this way, like it will be 30. And like same way, like you can do till the end, like, and you will get some values and see like what is the answer. This because like it's already 8, so I'll need to speed up things. So you can do this in similar manner, like you can do this. Like just keep on calculating TD updates and see the answer. So which one of the following statements are true for SASA? So which of the following are true? Like, is it like it uses bootstrapping to approximate? Yeah, definitely bootstrapping is there, R plus gamma times some value. So it is on policy. Yes, you know it. It is a TD method. Is it a TD method? Yes. It always selects the greedy action choice. Is it always, or you can use something like epsilon greedy, which we have already done, so you can get the answer from this one. Okay, so if there is any doubt in any of these questions, you can ask me now. Otherwise, like I'll move to next slide, which is the reading material. So maybe I'll check chat once. Okay, there is no doubt. So like basically like this is the link of Sutton and Bartow book. So chapter 5 was Monte Carlo, like it's done. Chapter 6 was these TD methods, like TD0 specifically, Q learning and SASA. This is also done. And also like in book, there is expected SASA. So you can read up that also. And if possible, you can code it up also. There's not much change which you need to do so that you have the algorithm in book also, you just need to code it up. And this is the like these are the like 4 other papers of upper confidence trees, TD methods, and SASA and Q learning. So you can go through them, but one thing to note is like they might follow a different notation that we are from the one which we are following in classes. So this you have to be careful. If you are interested, you can read these papers also. So yeah, I think that is it from my side today. So if there is any doubt or anything, you can ask me now. So as usual, like last week was an exception because like we had week 5 on Friday. But from now on, unless specified, like we will generally have these sessions on week 7 onwards. Like it will be Tuesday and same time, 6 to 8, and same link also. So last uh in week 5, what happened? Like I like the link which was shared was broken actually. So due to that, like people couldn't join on Friday session. But like now that link has been restored. So either way, like you can find the link in this. I have already pasted this link in the second slide. So this is always there. So maybe you can go to that spreadsheet and find that these slides and get the link from there. If in future, like sometimes the link is given is broken. Okay, so I think that's it from my side. If there is anything, you can ask me in chat. Okay, yeah, welcome. Otherwise, like for also for like the next one will be on TD lambda. So next week's lectures of week 7. So this is like Q learning and SASA are like the most popular learning algorithms. And these are like TD zero control algorithm. So this zero like is like corresponding to this lambda. Lambda is the like family. You can have lambda equal to 0, 1, and in between also. So this is the general family of TD lambda algorithm. So this general framework will be introduced in week 7. And in those algorithms, you can plug in this value of 0 and get these algorithms. So there are concept of traces, eligibility traces. So there is some rigorous mathematics involved there in this TD lambda algorithm. So it's better, like I would suggest that after watching the lectures, you try to read book also, which will be chapter 7. So it will actually help you, like, because this TD lambda is not straightforward topic. So you might need to do it once or twice to actually understand it. So I think like that is it from my side. So I'll be sharing this these slides and code also with you. So yeah, can I get your email for getting some doubt cleared? Actually, like email, like we are not supposed to share, but that forum is there. Maybe I'll do something about it. Maybe I'll check that forum. Because see, like the thing is like the email ID which we use for registering to NPTEL course, like we haven't registered to for the course using that ID. So we can access to some other ID, but then we'll have to see that the name and all is same. So I'll check that and I'll talk to NPTEL people if there is something for that. Maybe like I'll check those doubts also in full. Okay, so I think that's it from my side. So now I'll stop recording. Okay, so now the recording has to stop. Okay, I have stopped the recording.